Hello, I'm Lisa Whirlidge from the Bat Conservation Trust in the UK. I'm lucky that I get to work with some amazing bat researchers from the Global South on international groups such as the IUCN Bat Specialist Group and through GBATnet. There are over 1,400 bat species in the world today, and conservation of these amazing mammals is my day job. But the evolution of bats and their great diversity is absolutely fascinating. I'd love to study bat evolution if I had my time again, and this is reflected in my choice of paper for this Advent video. It touches on one of the reasons that bats are so special. Despite the myths about flying reindeer, there is only one group of mammals capable of true flight: bats. The lead author of the paper I've chosen is Lucila Amador, based in Argentina. Her co-authors are B Simmons Norberto Giannini. The topic is the aerodynamic reconstruction of the primitive fossil bat Onychonycteris finneyi, and was published in Biology Letters back in 2019. This bat is one of the oldest known species, having been around in the early Eocene, 52.5 million years ago. Bat fossils from the Eocene are known from every continent except Antarctica, a global distribution we still see in bats today. Whilst Onychonycteris finneyi was clearly a bat, the authors highlight its relatively primitive features. The proportions of its limbs and the presence of claws on all wing digits suggest that it may have been a more agile climber than any other known bat species. This is the first paper to attempt a detailed aerodynamic evaluation of this ancient bat. It weighed about 40 grams. The authors estimated basic aerodynamic features from carefully reconstructed aerofoils of the two known specimens and compared these with a wide example of extant species. This included measuring wing loading, the weight of the bat divided by the wing area, and the aspect ratio, which is the square of the wingspan divided by the wing area. The first figure of the paper shows images of two fossils: the holotype used to first describe Onychonycteris finneyi and the paratype. These are placed alongside the author's digital reconstructions of the aerofoils from the fossils, with the wings extended. Key measurements and areas of the hand wing and arm wing are highlighted. The next step the authors took was to manipulate the aerofoil structure by removing the hand wing in order to evaluate its contribution to various aerodynamic variables, and to compare the species with gliding mammals. The researchers predicted that Onychonycteris would compare poorly with other bats in terms of these basic variables, and that removing the hand wing from the reconstructed aerofoil would bring the species closer to the aerodynamic morphospace of gliding mammals. The aspect ratio value for both fossil specimens was found to be one of the lowest known in bats, whereas the wing loading far exceeds the median and the mean for extant species. The results from this analysis are shown in Figure 2, with the plot of the aspect ratio against wing loading, including not only extant bat species, but species of gliding mammal and 7 other fossil bats from the early Eocene, in addition to Onychonycteris finneyi. All the extinct taxa fell within the realised morphospace of extant bats, although Onychonycteris was in the lower boundary of this space. When the authors took away the hand wing and considered just the arm wing, aspect ratio was lower and wing loading was much higher, putting Onychonycteris much closer to the gliding mammals on the plot of aspect ratio and wing loading. Based on their analysis, the authors suggest that Onychonycteris has no aerodynamic equivalent, but rather exhibits a unique and comparatively inefficient combination of very low aspect ratio and very high wing loading for its probable weight. They interpret the bat's aerofoil structure as being primitive and state that's in keeping with the ancestral position of other morphological characters of the species, such as the presence of claws on all the digits. From their reconstruction, the authors determined that Onychonycteris would have had to fly very fast in order to generate enough lift for its weight. This would have been very costly in energetic terms, with Amador and her co-authors estimating the power required to sustain level flight being 25% as much again as a similar-sized extant species. Onychonycteris most probably used flight for commuting between roosting points and foraging sites. The authors infer that it wasn't a manoeuvrable species. They suggest it might have had an undulating flight style involving alternating flapping and gliding, saving energy during gliding phase. The authors explain how the evolution of the hand wing, in addition to the arm wing, bridges the aspect ratio gap between gliding mammal species and bats. They propose that evolution of the hand wing by a developmental mechanism promoting digit lengthening would have enabled a gliding bat ancestor to reduce wing loading, so decreasing velocity whilst gaining manoeuvrability, and to increase aspect ratio, which enhances aerodynamic efficiency, reducing the energetic cost of flight. All of which supports a gliding hypothesis for the early origin of bat flight, first theorised by Charles Darwin. This paper is a real treat for anyone interested in the evolution of bat flight. It's highly accessible, well written, and perfect reading for the holidays.